All right, so we finished the last lesson in limbo. We know the Bohr model no longer works because electrons act like waves, and we have this uncertainty principle. And we no longer know where things are, and that just creates uncertainty. But then along comes Schrodinger, and Schrodinger writes his equation to create a model of the atom. And it's all based on probability. You know, it's kind of like if someone were standing outside of my classroom and they couldn't see through the door or through the window, and they had to guess where I was in the classroom. If it's during class time, most likely I'm in front of the board. Probably 90% of my time during class time is spent in front of the board. Okay. Sometimes I walk around with my students. Sometimes I run over to my desk. Sometimes I go somewhere else. But majority of the time I'm going to be in front of the board. So you know probably where my location is. And that's what Schrodinger's equation does. It gives us kind of a 90% probability of where we think the atom is. And this creates what we call the quantum mechanical model, and it has 4 key parts. So principal energy level, sublevels, orbitals, and electron spin. So this fancy little shape over here is just showing you where the probability is that electrons are located. And you notice it got some really funky shapes there. We'll kind of get to that as we go along. So starting with the first one, the principal energy level. It is essentially the same as the energy levels in the Bohr model. That we got 1, 2, 3, 4, 5, 6, 7, 8 rings. And we can kind of think of energy levels doing the same thing. They are also related to the periods or rows on the periodic table. That principal energy level 1 is row 1 on the periodic table. Row 2 is principal energy level 2. Starts getting a little weird when we get down to 4, but period 4. But we'll deal with what weirdness goes on there. So principal energy levels are the simplest of the things. All right, second, sublevels and orbitals. So the principal energy levels are divided into sublevels. And there are 4 types of sublevels: S, P, D, and F. I don't know where the letters come from, but that's what they named them. I'm assuming it has something to do with German, since Schrodinger was German. So then these sublevels are then divided into orbitals. You don't need to worry too much about the L and the M sub L. That's for if you want to get into what are called quantum numbers. You can deal with that. But that's the symbols that go with them. So we have our sublevels, S, P, D, and F. Now, so if you have an S, it only has 1 orbital. P's are divided into 3 orbitals. D's into 5, F's into 7. So if you can remember S, P, D, F in order, the number of orbitals is just consecutive odd numbers after, so 1, 3, 5, 7. Consecutive odd numbers. And then shapes. S's are sphere shaped, like that. P's are dumbbell shaped, something like that. Most 4 of the D's have what we call a 4-leaf clover orientation that looks something like this. The 5th one's a little weird. And then F's are just wonky, weird. You get donuts and rings and other weird shapes like we saw on the previous slide. Okay. So F's are just complex. We don't really worry about their shape so much. All right, so that's sublevels and orbitals. So each energy level can be divided into sublevels. Those sublevels are then divided into orbitals. And those orbitals are here. All right, this will all kind of come together when we start doing this a little more specifically. All right, so electrons. Each orbital can hold up to 2 electrons. All right, so remember S's have 1 orbital, which means can hold 2 electrons. P's have 3 orbitals, and they can hold 6. D's have 5 orbitals, meaning they have 10 electrons. F's 7 with 14 electrons. All right. This seems arbitrary or random when I say this, but what's amazing is these sublevels correspond to blocks on the periodic table. That if I take my periodic table, my S block is right here. 2 electrons across. This is my first electron for S, that's my second. I'm looking for something 6 electrons wide. Oh, that's over here. Here's what we call the P block. Okay. Notice hydrogen's blue because helium kind of technically goes there in terms of quantum mechanics. All right, so here's my P, what we call the P block, because this corresponds to the P sublevel, and it's 6 atoms across. D can hold 10 electrons. That's this group here. We call this the D block because it's 10 atoms across or 10 electrons across. And then F's are these crazy guys down here. And if you're not familiar with this F block, they go right here. But in order to make the periodic table not be twice as wide, they bump them underneath instead of inserting them here. Okay? So they're not inserted here, we just bump them down here in order to save space. All right. Like I said, this video, like I said in the first video, quantum mechanical model is a little complex. You may need to watch this a couple of times. Watch it through all the way through first, and then watch it a second time, and I think things will make a little more sense once you see everything as a whole. So we need to figure out how, the whole point of the quantum mechanical model is to figure out how electrons are configured, or how they're arranged, how they behave. And so we're dealing with electron configurations. We got 3 rules. First rule is called the Offball Principle. Offball is just a German word for to build. And it just simply says we have to build the lowest level first before we can move on. And this is based on energy. So like when you're building with blocks, you can't build the second level of blocks until you build the first. Okay, so it's not like I can make this roof section and expect it to stay there if I haven't built what's underneath it. And so the Offball Principle works the same way, that we have to build our blocks on the lowest available level first, and then once we build that level, then we can build the next level. And then after that level, we can build the third, and then we can build the fourth and the fifth. But you can't do it until you do what's underneath first. Okay, that's what the Offball Principle means. Pretty simple principle. All right, these are your sublevels. Okay, notice, so the number corresponds to the principal energy level, 1, 2, 3, 4, 5, 6, 7. And then the letter corresponds to the sublevel. So there are 7 different S sublevels. And the way we distinguish between them is the number in front. So 1S, 2S, 3S, 4S, 5S, 6S, 7S. Same thing with P's. We got 6 different P's, 4 different D's, and 2 different F's. Once again, that corresponds to, if you look at the periodic table, the S block has 7 rows to it. The P block has 6 rows. The D block, those transition metals in the middle of the periodic table, have 4 rows. And then the F blocks at the bottom have 2 rows. Once again, it corresponds to what we have on the periodic table. So when we fill these up, we have to fill them in order. And this diagram shows you how to do it. It's done with these diagonal arrows here. Is that we don't just simply go 1, 2, no, we don't just go across like this. Because energy-wise, it doesn't really work that way, because the weird one happens here. This is where it first happens. 3D is actually after 4S. And that's because 3D's energy is a little bit higher than 4S's energy. And so we do 4S first, then we do 3D. We'll look at some examples of how that plays out more later. It'll make more sense when you see it being used. All right. We have Pauli's exclusion principle. Pauli's exclusion principle states that when we have 2 electrons sharing an orbital, they must spin in opposite directions. Remember, each orbital can have 2 electrons. That just says we have to write them in spinning opposite directions. By convention, the first electron to go into an orbital spins up. We say the second one spins down. And you can draw them as full arrows or half arrows. This is the most common way of doing it, just because chemists are lazy and it saves time. And so we do 2 half arrows instead. All right, third one, Hund's rule. If possible, electrons prefer to be unpaired over being paired. So what this happens in P, D, and F sublevels. Because in an S, you only have 1 orbital, so they don't have anywhere to go. But so, for example, this is a P. So I've got 3 orbitals, and I'm going to put electrons in here. And the electrons are going to go in. So the first guy goes in, he's like, hey, I'm going to go here. Second one goes there, third one goes there, then the fourth one finally pairs up. Because they're going to try to be unpaired first. So let's look at this a different way. Say this is a 3-bedroom apartment. And you got heterosexual males moving in. Okay? So the first guy goes in, he's like, all right, 3 free bedrooms. I'm taking that one right there. Second guy moves into the apartment. He's like, I can share with the first guy, or I can get a second bedroom all to myself. Let me think about this for a second. No brainer. Second bedroom all by myself. Third guy moves in. I could share a room with the first 2 guys, or I could get this third bedroom all by myself. Oh, I'm going to take the third one all by myself. When the fourth electron comes in, then they have to pair up. So this is what Hund's rule says. It's all it's saying is that when they fill in, they're going to take the rooms individually first before they start pairing up. And then they will pair up accordingly. Okay? And so that is the gist of Hund's rule. All right. So let's look at an example. Oxygen. Oxygen has 8 electrons in it. This is atomic number 8. And remember, we're generally going to assume that electrons are equal to protons, because we're dealing with neutral atoms here. So what we're going to do is we're going to start with 1s, and we're going to just keep going until we've accounted for all the electrons. All right? So 1s. 1s has 1 orbital, so we draw 1 dash. And then it can hold 2 electrons, so we put 2 electrons there. After 1s, if we look at our filling diagram here, after 1s, we get to the end of this arrow, we go to the beginning of this one, we go down, so we go to 2s next. And after 2s, we'll get to 2p. And then we would keep going if we need to. So after 1s comes 2s. Put a big enough space there that you don't confuse them as being the same. So 2s, and then we put 2 electrons in there because it has 1 orbital, meaning it gets 1 dash. And we fill it up with 2 electrons. So that's 4 electrons down. And then we get to 2p. And the way you do a p is you write the 2p under the middle one, and you draw 3 dashes for the 3 orbitals. Once again, leaving a bigger space here to distinguish, and then a small space here to show that these go together. And I've got 4 electrons left. And by Hund's rule, first one goes here, second one, third one, and then fourth one goes there. Okay, I've now drawn all 8 electrons, and that is the electron configuration for oxygen. And we call this drawing the configuration, all right, because we're drawing dashes and arrows and all that kind of stuff. All right, let's do something a little bit bigger. Let's do manganese. Okay, manganese has 25 electrons, and we're going to do the same thing that we did with oxygen. We're going to start at 1s. We're going to keep on going until we've accounted for all the electrons. And so we start at 1s, then 2s, 2p, 3s, and we get to 3p. We've now accounted for 6, 12, 14, 16, 18 of its electrons. So we have 7 more to go. So looking at our filling order, after 3p, we go to 4s. We do not go to 3D. We got to follow the arrows. So after 3p, we're going to do 4s. And then after 4s, we get to 3D. And we get to 3D, we got 5 electrons left. So we had 7 left. There goes 2. We got 5 more left, and we fill them into the Ds. And once again, because of Hund's rule, we simply put them in, all of them going up in the same direction, nobody sharing an orbital. All right, so there are ways to make this go faster. If we had to do this and count electrons every time we had to do this, it would be mind-numbingly slow. But we can use the periodic table to make this go faster. So for example, let's look at the configuration we did for oxygen. The last sublevel is 2p, and there are 4 electrons in it. If we look at the p block on the periodic table, oxygen is in the p block. It's in the second period, or the second row, and it's the 4th one over. 2, 2. P, P, 4, 4th. Okay? So we can use this to help us do this so much faster. Okay? Because this will help us to know where we stop filling the configuration. That we know that oxygen's in 2p and it's the 4th one over, so we know that's where we're going to stop. But here's the beautiful piece about it. Because of the off-ball principle, remember it said that we got to build the lower floor before we can build this next one and so on? So according to the off-ball principle, before we get to 2p here, we had to have already done these two. And we already know they're full. So everything before where we stop has to be full. Okay? So we can do the same thing with the manganese one that we just looked at. All right? Manganese is in the 4th period. So if we could see over here, this would be the 4th row, or the 4th period on the periodic table. It's in the D block, and it's the 5th one over. Well, but if we look at the configuration, it's 3D, not 4D. And that's because the number of the D sublevel will always be 1 less than the period number. Okay? So even though I'm in the 4th row, that's 3D. If I was in the 6th row, the D block there would be 5D. It would be 1 less. Okay? So this means that we're in 3D, 5th one over. So 3D with 5 electrons is where we're going to stop. Everything before that on our filling order has to be full. And so this just makes it so much faster because we can just use the periodic table to tell us where we stop. Okay? And once again, this is called drawing a configuration. We can also do what is called writing them. Writing a configuration simply takes what we had as the arrows and dashes and converts them into writing the sublevel and then a superscript. So looking at oxygen, 1s with 2 electrons in it, so we write 1s2. 2s has 2 electrons in it, so we write 2s2. And then P has 4 electrons in it, so we write 2p4. Same thing with the manganese. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. Once again, since we know this is where we stop, we know all of these have to be full, which means all the s's have 2 electrons, and all the p's have 6. Okay? So like I said, all of them except for the last one will be full. This makes life relatively easy for us. Okay. All right. Writing configuration for large atoms is cumbersome, so we need a shorter method. It's called noble gas configuration. Noble gas configuration is purely optional. You don't have to do it. You don't have to teach it. And so we're looking at manganese's configuration here. Missing an S after that apostrophe, but anywho. So we got its configuration there. 1s2, 2s2, 2p6, 3s2, and so on. So the noble gas configuration starts by looking for the noble gas that ends the period above the element. Okay, so manganese is on the 4th row, or the 4th period. So we need to look at the end of the 3rd period. At the end of the 3rd period is argon. So argon is the last element in 3p. So we can rewrite everything from 1s to 3p as argon. So because all of this, that's the configuration of argon. And it's at the end of the row, so it's a good place to stop. So we take all of this, rewrite it as argon in brackets, and then continue the configuration from there. For manganese, that's not so bad. But let's look at something significantly larger. Okay? Let's look at lead. Lead is in 6p2. It's in the p block, the 6th row on the periodic table, and it's the 2nd one over. So it's at 6p2. So if we go to the end of the 5th period, the end of 5p, we find xenon. We can then use xenon to write the filling order all the way from 1s all the way to 5p, and then we can start after that to finish the configuration. So you would start with xenon And we know xenon's at the end of 5p. So we can look at our filling diagram, the thing with the diagonal arrows, and we know that we can start right after 5p, which is 6s. And then we can continue on from there. Once again, because I'm in 6p2, I know everything before that's full. Every s has 2, every p has 6, every d has 10, and any f's we do would have 14. The F block itself is a little funky. So we try not to do too much with it. There's a couple in your workbook, and the key will kind of explain why they are what they are. The only way to learn how to do electron configurations is to do them. You can't simply watch me do it, but I would encourage you to watch this quantum mechanical model video one more time to kind of get a hold of what's going on and why, and then start working through the workbook. And then use the key to check your work. And then if you have questions, email me, Facebook message me, or drop in for office hours, and I'll be glad to help you through this. Because remember, I'm here to help you out. So if you run into questions, if this is bothering you, you're not getting it, ask. And I will be here to help. So with that, go ahead over to workbook and get practicing these.